Hello friends, welcome back to the Electromagnetic Theory series. In worked example 1, we located a point in 3 coordinate systems. In worked example 2, we rewrote a vector field in those systems. Today, we meet the first differential operator of the course, the gradient. Imagine a scalar function f of x, y, z. Think of it as the temperature inside a room or the height of a hilly landscape. At any point, the gradient of f, written nabla f, is a vector that points in the direction where f increases the fastest. Its magnitude tells you how fast that increase is per unit length. One more key property: at every point, the gradient is perpendicular to the level surface, that is, the surface on which f is constant. If you hike perpendicular to the contour lines on a map, you are following the gradient. Today we will derive the formula for gradient in Cartesian, then compute it by hand on a simple example. Where does the formula come from? Start with the total differential. If f depends on x, y, and z, a tiny change in f is the partial derivative with respect to x times dx, plus the partial with respect to y times dy, plus the partial with respect to z times dz. Now introduce the displacement vector dl equals dx x hat plus dy y hat plus dz z hat. Then df is exactly the dot product of two vectors, the one with components partial f partial x, partial f partial y, partial f partial z, dotted with dl. That first vector is what we call nabla f. So in Cartesian, nabla f equals partial f partial x times x hat, plus partial f partial y times y hat, plus partial f partial z times z hat. 3 partial derivatives, 1 for each axis. That is the entire definition. The rest is arithmetic. Let's do it. Take the scalar field f of xyz equals x squared y plus z. Our point is q equals 1, 2, 3. We want nabla f at q. Step 1. Partial with respect to x. Treat y and z as constants. The derivative of x squared y is 2xy, and the derivative of z with respect to x is 0. So partial f partial x equals 2xy. Step 2. Partial with respect to y. Now x and z are the constants. The derivative of x squared y with respect to y is just x squared, and the derivative of z is 0. So partial f partial y equals x squared. Step 3. Partial with respect to z. Here x and y are constants. The derivative of x squared y with respect to z is 0, and the derivative of z is 1. So partial f partial z equals 1. Now evaluate at q, which is x equals 1, y equals 2, z equals 3. The x component is 2 times 1 times 2 equals 4. The y component is 1 squared equals 1. The z component is 1. So nabla f at q equals 4x hat plus 1y hat plus 1z hat. Its magnitude is the square root of 16 plus 1 equals the square root of 18, which is 3 root 2, about 4.243. Now let's see what this means. Fix z equals 3, so we look at f as a function of x and y only. The level curves, where f is constant, are the curves x squared y equals some constant. At our point, x equals 1, y equals 2. So x squared y equals 2, meaning f equals 5. A nearby level curve might be f equals 6, where x squared y equals 3, and another at f equals 7, x squared y equals 4. As f grows, the curves move outward away from the origin in the direction of increase. At q equals 1, 2, 3, if we project onto the xy plane, we sit on the curve f equals 5. Our gradient at q has an xy part of 4x hat plus 1y hat. Draw that arrow starting at q, pointing mostly in the plus x direction and slightly in the plus y direction. Two things to notice. First, this arrow is perpendicular to the level curve at Q. That is a theorem, not an accident. The gradient is always normal to the level surface. Second, the arrow points from the f equals 5 curve toward the f equals 6 curve, that is, in the direction of increasing f. That is why we call it the direction of steepest ascent. The z component, which is 1, lifts the full gradient slightly out of the page. It exists because f changes as z changes, even at constant x and y. Quick recap. The gradient of a scalar field in Cartesian is partial f partial x x hat plus partial f partial y y hat plus partial f partial z z hat. Geometrically, it points in the direction of steepest increase and is perpendicular to the level surfaces. For our example, f equals x squared y plus c, at q1, 2, 3, we got nabla f equals 4x hat plus y hat plus z hat, magnitude 3 root 2. In the next worked example, we will do the same gradient operation, but in cylindrical and spherical coordinates, where the formula picks up factors of 1 over rho and 1 over r sine theta. See you then.